In the summer of 1944, as World War II had reached a decisive phase after the Normandy landings on June 6th, the Nazi High Command launched one of its desperate efforts to reverse the course of the war with a promising new weapon, the V-1, also called the revenge weapon, Vergeltungswaffe 1. The V-1 was not a piloted aircraft, but an early cruise missile designed to take off from land and fly a preset distance to its target. It carried a heavy warhead and could be launched in large numbers, promising significant damage to British cities without putting German soldiers' lives directly at risk. The V-1 was developed at the Peenemünde Weapons Research Center and later mass-produced at several facilities, including underground factories that used forced labor from concentration camps, a dark reality embedded in the Reich's story of wartime technology. Technically, the V-1 was simpler than a bomber, an aerodynamic fuselage, fixed wings, an Argus S-109 U-14 pulsajet engine, which produced its characteristic buzzing sound, basic automatic guidance, and a distance measuring device to program the point of impact. A V-1 weighed a little over 2 tons, carried roughly 850 kilos of explosives, and traveled at about 640 km/h at altitudes ranging from a few hundred meters to over 2,000 meters depending on the launch trajectory. These characteristics made the V-1 a difficult target for conventional anti-aircraft defenses and for interceptor aircraft at the time. German planners calculated that, with a relatively low production cost per V-1 compared with manned bombing missions, a V-1 campaign could exert significant strategic pressure on British civilian populations and infrastructure, undermining morale and the enemy's capacity to continue the war without costing German lives. That strategic thinking was intertwined with the expectation that control and manufacturing technologies would allow mass launches, an industrial rain of bombs from the continental mainland. The first operational use came soon after D-Day. On June 13, 1944, the first V-1 fell on London, damaging roads and bridges and killing some civilians. It marked the start of a series of attacks aimed chiefly at the capital and other densely populated areas. German leaders, including engineers at Peenemünde and military planners, believed the V-1 would be an effective reply to setbacks on the European fronts. A kind of revenge weapon that could severely damage British public confidence and force the government to reallocate defensive resources. From the British and Allied perspective, awareness of the V-1 triggered a rapid chain of responses: radar early warning, ground-based anti-aircraft systems, and especially the deployment of pilots assigned to hunt the V-1s. Air interception of the V-1 was possible, but required very specific measures. Interceptors had to reach sufficient speed and maneuverability to close with rockets traveling around 640 km/h, while avoiding being caught in the blast if they approached too closely. Meanwhile, conventional anti-aircraft artillery faced a difficult probabilistic problem. The V-1 was compact, fast, appeared suddenly after detection, and followed a relatively flat trajectory, so scoring a direct hit with unguided shells was rare. Early calculations showed that the hit probability using standard artillery without special technology was extremely low, making reliance on traditional guns alone unsafe for protecting major cities. In that context, Britain and the Allies organized an integrated defensive response, deploying radar networks for early detection, stationing belts of anti-aircraft guns along the coast to intercept missiles crossing the English Channel, intensifying fighter squadron interception missions and adjusting tactics. Gun positions, especially those on elevated ground in southern England, such as the North Downs, were redeployed to form dense defensive rings close to the coast to ensure that if a V-1 was missed or failed to detonate, completely its wreckage would fall into the sea rather than back into German hands. These improvements were not immediate, but resulted from coordination among intelligence, tactical trials, and the stepwise application of technical upgrades. For Germany, the V-1's arrival was both a source of pride and scientific achievement and a deep concern. German engineers, with their strong traditions in physics and mechanics, believed that a cheap, mass-produced automatic system like the V-1 would be hard to defeat with conventional air defenses. They relied on the design's simplicity and numbers to maintain continuous pressure on targets. Yet the battlefield is not only a testing ground for new weapons, it is where adversary responses, production limits, logistics, and technological security vulnerabilities are exposed. While Germany focused resources on producing and launching V-1s, much of it carried out by forced labor under harsh conditions in underground factories, The Allies simultaneously exploited advantages in industrial capacity, scientific research, and mobilizing civilian resources for war production. Thus, the story of the V1 is not merely the story of a single weapon, but reflects a larger conflict between two models of warfare. One based on miracle weapons developed under concentrated expertise but limited output, and the other built around mass production and broad application of technologies that enhance combat effectiveness. When the V1 campaign began, both sides were testing their assumptions. Germany hoped the strategic effects of the cruise missile would compensate for losses on other fronts. The Allies, while trying to reduce civilian casualties, also had to rapidly develop countermeasures to stop the new threat. The weeks and months that followed would show that detecting, intercepting, and ultimately undermining the V1 strategy was not simply a technical problem of hit or miss, but a race for superiority between mass-produced technological improvements and efforts to gather and analyze intelligence and refine tactical experimentation under conditions of total war. In the early weeks of the V1 campaign, the flying bombs seemed to bring a new wave of fear to the British. They appeared in large numbers at dawn, following relatively flat, high-speed trajectories, which made detecting, tracking, and destroying them in a short time a major challenge for traditional air defense forces. However, the British and Allied response did not rely on miracles. They organized an integrated air defense system, improving both tactics and technology, which rapidly increased interception effectiveness within just a few weeks, eventually reaching levels that were nearly unbelievable from the perspective of German engineers. The first step was redeploying forces and establishing defensive belts. Anti-aircraft units no longer remained in fixed traditional positions but were concentrated into dense gun belts along the southern coast of England, the area the V1 had to cross from continental Europe. The objective was practical: to prolong the engagement time between the target, the V1, and the air defense network, while ensuring that any V1 shot down would fall into the sea rather than into populated areas or be recovered for analysis by the enemy. Moving the batteries to the coastal line also reduced civilian risk and allowed tighter control over any wreckage. Such tactical adjustments provided the necessary framework for technical improvements to take effect. Second, air defense capability was enhanced with radar and automatic fire control systems. From the start of summer 1944, British anti-aircraft units, along with U.S. supplied units, deployed SCR-584 fire control radars coupled with the M9 gun director developed by Bell Labs. The SCR-584 was a centimetric radar capable of high-precision target tracking, while the M9 director was an analog computer continuously calculating firing solutions for gun batteries, updating parameters such as target trajectory, speed, wind effects, and shell characteristics. When combined with proximity fuse shells, VT fuse, the system became a highly effective semi-automatic air defense setup. Radar locked onto the target, the director computed the firing solution, and the gun crews merely loaded and fired according to electronic commands. The SCR-584 plus M9 combination turned anti-aircraft guns into a reliable tool against small, fast targets like the V1. Alongside the gun belts, Allied air forces implemented active interception tactics. Initially, pilots struggled to chase near-sonic targets, but experimentation led to two main methods for taking down V1s: direct fire destruction and an indirect trick technique. For direct fire, aircraft were modified for high speed and low altitude maneuverability, most notably the Hawker Tempest, Supermarine Spitfire MK, North American P-51 Mustang, and boosted variants of the Republic P-47, tasked with intercepting V1s along the final approach before they reached inland areas. Some Tempest squadrons operating from bases near the coast achieved notable success. Between mid-June and early September 1944, they claimed the destruction of large numbers of V1s, with some squadrons and individual pilots credited with dozens of kills. Additionally, a unique technique was developed and passed between units, using the aircraft wing to tip the V1's wing. Because the V1 relied on a gyroscope for stability, lightly lifting one wing by the airflow, caused by a gentle wingtip contact, would disable the gyroscope and disrupt the control surfaces, sending the missile crashing into the sea or falling harmlessly without detonating near the plane. This method was risky but effective. Many inventive pilots used it when ammunition was low or interception distance was too short. These wingtip maneuvers became part of the British air defense experience in dealing with cruise missiles. The combined effect of these efforts, redeploying guns, Deploying SCR-584 radar with M9 directors, using VT Fuzes, and enhancing air interception tactics produced a leap in air defense efficiency. Wartime statistics reflect this dramatically. From an initial destruction rate of only a few percent, the percentage of V-1s destroyed by gunbelts and air defenses increased weekly, reaching around 60% by August 23, 1944, and continuing to climb until, on a notable day in late August, coastal gunbelts achieved an 82% interception rate before V-1s posed a threat to London. These figures astonished German engineers. They observed V-1s being destroyed in ways that traditional ballistic calculations suggested were impossible, leading to misguided theories about new control devices, espionage, or even sabotage. Another important change was ammunition efficiency. Before the integration of VT fuses and automatic directors, destroying a single V1 required thousands of shells. After incorporating the new technologies, the number of rounds needed dropped to just a few dozen or roughly 100. This not only conserved resources but allowed gun crews to sustain fire over extended attacks. As a result, air defense units no longer had to compromise effectiveness due to ammunition concerns or crew fatigue. They could maintain precise pressure on V1 streams throughout the night and into the early morning. Beyond the direct impact on V1 losses, the integrated air defense system had a significant psychological effect. Knowing a dense defensive barrier existed, causing many V1s to be destroyed before reaching their targets, reduced civilian panic and maintained the morale of the British government and armed forces. At the same time, repeated failures of V1s to reach their objectives forced German commanders to adjust launch methods, test new sites, or switch to nighttime tactics to evade radar, actions that consumed time, resources, and diminished the strategic effectiveness initially envisioned for the V-weapons program. In short, this unexpected effectiveness was not a miracle from a single factor, but the product of integrating multiple elements. Tactical redeployment, precision fire control radar, SCR-584, fire control computers, M9, proximity fuses, and flexible air interception tactics. When these pieces worked together, they created a highly coordinated defense system, turning the V-1 from an apparently unstoppable threat into a much more manageable target. And it was precisely this leap that caused interception rates to soar during the summer of 1944. The proximity fuse, commonly abbreviated as VT, variable time fuse or proximity fuse, was one of the key technological inventions of World War II. Not because it was an incomprehensible, futuristic idea, but because turning that idea into a compact, durable, mass-producible electronic device under wartime conditions was a true engineering feat. Fundamentally, a VT fuse functions like a small brain mounted on a shell. Instead of counting time or measuring a mechanical component to detonate at a predetermined moment, the fuse continuously emits a radio signal and listens for reflections from large objects in the surrounding area. When the intensity or characteristics of the reflected signal indicate that the warhead is near the target, whether an aircraft, missile, or naval vessel, the control circuit triggers the detonation mechanism. The result is an explosion at an optimal distance for shrapnel to disperse and damage the target, even if the shell does not strike directly. While this concept sounds simple, integrating the radio transmitter receiver system, processing circuits, switching components, and a battery into a small volume, and making it survive being fired from a gun barrel under extreme acceleration was something pre-war engineers considered nearly impossible. The technical challenges were multifaceted. First, there was the issue of extreme mechanics. A shell leaving a gun barrel experiences acceleration tens of thousands of times that of gravity, g, while simultaneously spinning at extremely high speeds, tens of thousands of revolutions per minute due to barrel rifling. Conventional electronic circuits and vacuum tubes of the era could hardly survive these forces. Most standard tubes would break or lose contact during acceleration. A crucial part of the project, therefore, was developing miniaturized, reinforced vacuum tubes capable of withstanding shock and vibration while maintaining stable electrical performance. Simultaneously, engineers had to design a small battery capable of instant activation after months of storage. The battery could not degrade over time but had to start up and provide enough power to operate the transmitter and detonation circuit in the final seconds before impact. Next was integrating the antenna and transmit-receive system into the Fuze's compact cylindrical body so that it would function effectively while spinning at high speed. Technical solutions had to balance antenna size, radiation direction, and reflected signal detection in complex environments, air, debris, water, etc. The circuit also had to distinguish true target reflections from background noise, a signal processing requirement that was far from trivial with analog technology at the time. Designers addressed this using frequency filtering, selective amplification, and fast-switching devices, such as thyrotrons, to recognize the characteristic reflection patterns of large targets. Production challenges were equally formidable. A device that worked in a laboratory with a few dozen prototypes did not automatically translate into the ability to manufacture hundreds of thousands or millions in a short period. Most effort was devoted to component standardization, rigorous quality control, and testing. Every production batch of fuses underwent electronic checks, and random samples were fired from test barrels to verify resilience under acceleration. The reject rate had to be kept very low to ensure both combat effectiveness and material efficiency. This required mobilizing the entire civilian electronics industry. Factories producing vacuum tubes, batteries, and electronic components were adapted to military standards. Leveraging large civilian companies for the war production line, e.g. light bulb, radio, and household appliance manufacturers. And adopting modular production methods were key to bringing the VT fuse from laboratory to battlefield. Secrecy was an essential part of the entire program. The VT fuse became a decisive weapon partly because Hitler and German scientists were unaware of its existence and operational principles during the V1 attacks. Consequently, production and operational teams were under strict orders to maintain maximum secrecy, from packaging and inventory control to deployment policies. VT fuses were distributed to anti-aircraft units under tight regulations. Duds had to be recovered immediately and secured to prevent enemy access, since an intact fuse could reveal the technology. In some cases, batteries were instructed to arrange for unexploded shells to fall into the sea rather than on land. This secrecy was not merely a military concern, but also a tactical and ethical consideration. Limiting use on the continent sometimes exposed friendly forces to greater risk, but commanders judged that preserving technological secrecy would yield greater long-term advantages. On the European battlefield, the practical impact of the VT fuse was clear when integrated into the air defense complex described earlier. SCR-584 radar-tracked targets, fire control devices, calculated firing solutions, and VT-fused shells detonated at an optimal distance around the V1. Even near misses, which would have been ineffective with conventional fuses, could now destroy the missile because the explosion occurred within the lethal radius. This dramatically reduced the number of shells needed per target, a pivotal improvement for sustaining air defenses during concentrated attacks. VT's naval application also altered the balance in the Pacific. Anti-aircraft shells with VT fuses protected surface ships from attacking aircraft, significantly increasing fleet survivability in naval battles. However, VT development and deployment also had broader strategic and policy implications. Concerned that some fuses could fall into enemy hands and reveal operational principles, the U.S. military initially restricted VT use to certain theaters and weapon types. Its deployment in ground artillery for infantry operations was carefully considered and expanded only when the technology's secrecy was deemed secure. Once validated and secured, VT saw wider use, significantly contributing to casualty reduction and force preservation. After the war, when VT technology was declassified, its influence was evident, not only as an improvement in hit probability, but also as a precursor to modern military electronics applications such as distance sensors, compact radar, and automated weapon systems. In summary, the VT fuse exemplifies an era in which victory depended not only on the battlefield, but also in laboratories and factories. It combined ingenious physical solutions, sophisticated electronics, large-scale manufacturing capabilities, and high-level secrecy. Its success in countering the V1 and in naval engagements reshaped air defense thinking and drove technological advances well into the post-war period. An exemplary case of how a small, mass-produced technology, when employed strategically, could alter the course of a war. Turning a technological concept into a war-changing product required not only creative design on paper, but also a massive industrial supply chain, meticulous quality control, and a rigorous security system, and that is exactly what the United States achieved to mass-produce the proximity VT Fuze during World War II. From its early days as a laboratory prototype, to becoming a standard component of anti-aircraft and artillery shells. This process tells the story of how a civilian economy was transformed into a war industry, with dozens of factories retooling production lines and tens of thousands of workers, many of them women, mobilized for a task most had little knowledge of in detail. Technically, the VT Fuze demanded extremely small yet highly durable components, miniature vacuum tubes reinforced to withstand tens of thousands of Gs of acceleration and extreme rotational speeds. Batteries designed for long-term storage without self-discharge and capable of instant activation. Antennas, transmit-receive circuits, and switching devices that were both electrically efficient and mechanically resilient. All of this only mattered if it could be produced on a large scale with a low defect rate, a domain where American industry excelled. Civilian factories, from light bulb, radio, and refrigerator manufacturers to precision component workshops, were restructured to produce VT components to military specifications. Some major companies shifted their entire research and production lines to this goal. Plants such as Crosley, Sylvania, and others expanded output, recruited tens of thousands of workers, and operated 3 shifts to meet enormous demand. Sylvania, according to contemporary reports, transferred its entire vacuum tube research department to produce the new reinforced tubes, manufacturing hundreds of thousands per day. Other plants producing batteries, metal casings, and precision mechanical parts also ran continuously. By the end of the war, the U.S. had produced tens of millions of VT Fuzes. The historical record often cites around 22 million, with peak daily output reaching tens of thousands of units. Some contemporary sources record a peak of about 40,000 per day. Achieving these numbers was not merely a quantitative success, but also a cost miracle. Initial laboratory production was extremely expensive, but once the lines were standardized and optimized, the cost per unit dropped dramatically, from over $700 per fuse initially to a few dozen dollars by the end of the war. For example, roughly $18 per fuse in later stages, demonstrating how mass production made a previously costly technology affordable and strategically viable. However, high-quality large-scale production did not happen automatically. The U.S. government and military established a strict quality control system. Every batch underwent multiple inspections, from electronic and environmental testing to random samples fired under real conditions, to verify that components could withstand the gun. Barrels, acceleration, and vibration. Any batch that failed standards was rejected. Production processes were standardized to the point that each worker performed only a specific task, reducing errors and increasing efficiency. Field testing by firing samples was a critical part of this system, beyond bench tests. A percentage of fuses were actually shot from test guns to ensure survival under real acceleration, a measure engineers emphasized to prevent battlefield failures. Beyond technical aspects, arguably the most important factor in the VT program's success was planning and maintaining maximal secrecy. Knowledge of the fuse's operating principle could allow enemies to replicate it or develop countermeasures. The U.S. government and military implemented a strict need-to-know policy. Factory workers typically knew only their specific tasks. Technical documents were coded or fragmented, and distribution to the front lines followed secure protocols with strict inventory control. The name variable time, VT, was partly a misdirection. Even internal reports were sometimes deliberately vague to reduce the risk of revealing the device's true purpose. Labeling, packaging, and inventory procedures were strictly regulated. Receiving units were trained in special handling to minimize risk of damage and protect the secret. VT deployment policies were similarly cautious. Initially, the U.S. limited use to specific theaters, for example, prioritizing the Navy to protect ships at sea, because of concerns that captured fuses could be analyzed and copied by the Germans. In Europe, when the V-1 became a direct threat to British civilians, Anglo-American commanders decided to use VT fuses on anti-aircraft shells immediately, but still maintained restrictions in areas where the risk of enemy capture remained high. One precautionary example was deploying gun batteries along the coastline so that unexploded fuses would fall into the sea rather than on land, minimizing the chance that intact fuses would reach German hands. Recovery of duds was a priority. Naval blockades and clearance teams were deployed to locate and secure remnants, which were then transported to analysis centers under tight security. Such secrecy came at a cost. At times, it meant withholding the technology even from some Allied units on the front lines, occasionally forcing difficult decisions regarding soldier safety, for instance, delaying VT deployment for certain field artillery systems until secrecy was ensured. Socially, the VT production program reflected broad civilian participation in the war effort. Tens of thousands of women worked in factories and shifts, performing tasks requiring millimeter precision. Many workers did not know the final purpose of the products they were making, only that accuracy was critical to national security. Factory stories, higher wages, production innovations, deadline pressures illustrate that the war was not just fought by soldiers on the battlefield, but also by industrial laborers in factories and warehouses. From a long-term strategic perspective, the ability to mass-produce VT fuses transformed the technology into a relatively inexpensive but highly effective weapon. When each fuse cost only a few dozen dollars yet could greatly multiply the effectiveness of a gun battery, the strategic value became clear. Large-scale production and strict secrecy were closely linked. Mass production reduced costs and enabled wide deployment, while secrecy ensured the technology could not be replicated before production capacity created an irreversible advantage. Ultimately, the combination of research, mass production, and information control allowed VT fuses to become a decisive tool on the battlefields where they were applied, including significantly weakening Germany's V1 campaign and laid the groundwork for how electronic weapons systems would be developed and deployed in the post-war era. The story of VT production is therefore not only a tale of technology, but also a lesson in how an industrialized society can mobilize resources, maintain secrecy, and optimize production to achieve strategic advantages on a global scale. When examining the direct consequences and strategic significance of the confrontation between Germany's V1 and the Anglo-American air defense system, the clearest insight is that the outcome was not merely a set of statistics on missiles shot down or civilian casualties, but a fundamental shift in how warfare was conducted in the 20th century. New weapons could create immediate crises, but the decisive measure of battlefield transformation was the ability to integrate science, engineering, and mass production. On a direct level, the V1 campaign from June to September 1944 saw approximately 9,521 missiles launched from continental sites toward England. Of these, only about 2,515 actually reached their target in London, causing thousands of casualties, but far fewer than Germany had hoped. Recorded casualties totaled roughly 6,184 dead and nearly 18,000 wounded. These tragic figures reflect the brutal nature of the weapon, yet they also demonstrate that the air defense system significantly mitigated the strategic impact Berlin intended. Without innovations such as radar, VT fuses, and automated fire control systems, the loss of life and damage to infrastructure could have been 4 to 5 times higher, according to estimates by some Allied air defense commanders at the time. In other words, technology changed the mathematics of war and saved thousands of civilians. Another consequence was that the V1 program became a strategic failure rather than a success. The material, labor, including forced labor from concentration camps, and technical resources Germany devoted to developing and producing the V1, instead of strengthening air defenses, fighter aircraft or frontline equipment were depleted with limited strategic return for the regime. The V1 consumed millions of Reichsmarks and thousands of workers, yet it could not force Britain to alter its strategy or break morale as the Nazis had hoped. Militarily, Germany was forced to adjust testing and launch procedures, seek new launch sites, attempt nighttime launches, or alter flight paths to evade radar and coastal gun batteries, moves that reduced campaign efficiency while consuming additional time and resources, yet yielding negligible results. This highlights the paradox of vengeance weapons. Though seemingly a cheap, scalable solution, they could be neutralized if the opponent possessed the right technology and organizational methods. A further strategic consequence stemmed from how the US and UK handled VT fuse secrecy. Concealing its operating principle and strictly controlling its use created a temporary but decisive advantage. Limiting VT deployment to certain theaters, prioritizing the Navy and Anglo-American air defenses, came at the cost of some soldiers and fronts not benefiting immediately. But strategic calculations showed that Preserving secrecy would yield greater benefits once production capacity allowed widespread deployment and the risk of enemy capture was minimized. The result was that VT remained secret until a critical stage of the war, helping the Allies gain an edge in Pacific naval battles and European air defense. From an industrial and social perspective, the VT program is clear evidence that industrialized war, the ability to mobilize a civilian economy to produce complex weapons, was decisive. The United States, with its extensive network of factories, engineers, and labor, converted production lines to manufacture tens of millions of VT fuses, reducing costs from extremely high early-stage prices to just a few dozen dollars per unit by war's end. This difference was not merely a technological story. It represented a fundamental distinction between a market economy capable of rapidly mobilizing labor and innovation, and a centralized economy with high scientific capacity but lacking large-scale production capability due to resource, logistical, and prioritization constraints. Thus, the victory over the V-1 was not simply a temporary military success, but a systemic one. A political economic system capable of mass-producing effective technology prevailed over a system producing technical masterpieces in limited quantities. Ethical and humanitarian consequences are also notable. Germany's V-1 program relied on forced labor under brutal conditions in underground factories, while on the Allied side, tens of thousands of workers, many women, participated in VT production under demanding but non-coercive conditions, receiving wages and some protective measures. This contrast underscores fundamental social differences between the sides and partly explains why American production capacity could exceed that of Germany, not only because of machinery, but also because of the workforce's mobilization. In terms of long-term technology, VT laid the groundwork for many post-war advances: compact radar systems, range-finding sensors, and electronics capable of withstanding harsh conditions. Principles and techniques were applied to radar altimeters, modern fire control systems, and a variety of civilian and defense technologies. VT declassification after the war also spurred research and applications in aerospace and electronics, contributing to post-war industrial leaps. An inevitable lesson for other nations was the importance of integrating research, production, and security policy. VT demonstrated that maintaining secrecy over a military technology could provide a strategic advantage if combined with production capability to exploit that advantage in time. However, it also raised ethical questions about limiting access to life-saving technology, even among allies, and the human cost of strict secrecy when it delayed deployment in certain theaters. Strategically, the V-1's failure and VT's development are among the first clear examples of the shift from wishful weapons or singular, catastrophic events to industrial scientific systems. Victory often comes from small, probabilistic improvements repeated millions of times rather than from a single high-yield weapon. Finally, the frustration and helplessness of German engineers, commanders, and leaders upon realizing that a small, cheap, mass-produced device had neutralized the V-1 program left a lasting psychological and intellectual legacy. Theoretical technological superiority was no match for industrial organization and policy. This stands as a historical lesson on the limitations of a centralized technological model without accompanying industrialization. In summary, the consequences of this confrontation were clear and multidimensional. The strategic effect of the V-1 was neutralized. Thousands of civilians were spared compared to worst-case projections. The Allied industrial scientific system proved decisive in modern warfare, and the world recognized that future military advantage would rely more on the capacity to produce and apply technology at scale than on a single wonder weapon.